I'm going to talk about double integrals. I'm going to assume that you've seen just a tiny bit, and in particular, how to do an iterated integral. And I want to take that in a little bit of a more general direction. So here's the geometric setup we have. I want to start out with the idea that a double integral could calculate a volume. It can calculate many, many other things, just like a single integral can calculate many other things besides the area under a curve. But this is the usual place to start. So I'm going to build a house in 3 dimensions as everything under a plane. So I've just drawn the part of the plane that lies in the first octant, like we often do. And that's going to be the roof, but that's actually more than the whole roof, because there's a floor plan for the house, which is the region over which we're going to integrate a function. And let's call that R for rectangle or region. And it's everything where x is from 1 to 3 and y is from 0 to 2. So it's all this stuff. And so let me draw that here. That's going to be kind of like this. And so it's going to be a house with this slanted roof and everything up here. So it's got a slanted tilty roof and a rectangular floor plan. And so it's kind of a box with just a slanted top. And the simplest interpretation of integrating this function that I've graphed here, and I'll show you the formula in a minute, over this region is the volume of that thing. Okay, so that's going to be the volume of the house, and we're going to write it as a double integral over the region, and I'm just going to call it region R at this point, of f of xy. I'm going to say dA. And it's a little bit different from if you've seen iterated integrals with like dy dx or dx dy, and there's an important conceptual change there. So let's just make it more explicit. This function, this graph is z equals 8 minus x minus 2y, as it turns out. So in this particular example, it's the integral over this region of 8 minus x minus 2y dA. So let me talk about what the dA means. So one way to do this is we need to slice this up or cut this thing up into smaller pieces in one way or another. And a way that takes advantage of one variable calculus, and it's the iterated integral idea that I have a separate video about, is to slice it up into either vertical slices or horizontal slices. And then that turns out to reduce to one variable calculus just done twice. And that's the idea of an iterated integral. But I want to focus on a different idea here, which is that there's many, many, many ways to slice up this thing into little bits. And kind of the more basic idea than the iterated integral is to sort of tile this floor into a bunch of tiny little rectangles. And so one little rectangle, a tiny rectangle, the picture's kind of small, I might redraw it. That, we're going to say the area of that rectangle has area delta A. And we could take that little rectangle, that's going to be a tiny little rectangle here, and we could just take the part of that house that lies over that tiny rectangle. Okay, so what is that going to be? Now, here's a good time to draw that bigger. We're going to get an object that's got a tiny little base. Compared to that, it's quite tall, and then has a slightly slanty or sometimes curvy roof, top to it. But the difference between this guy and, let's say, if we just kind of chopped it off and made it constant height, that's going to be a good approximation. This is very similar to thinking about the rectangle method, or the more fancy name is Riemann sums, for an integral in one variable. And so the volume over this floor plan under this function is going to a good approximation, especially if I cut this up really, really small, is going to be the sum over all those little tiny rectangles of, well, the area of the rectangle times the height. And I just have to pick some height somewhere in this rectangle to be representative and just declare the height of the whole thing to be that constant. So we could just call it like x sub I, y sub I, where I, it's the ith rectangle. And usually it's going to be a little bit decorated, a little bit more complicated than that. But I want to really just strip it down. So it's just a sum of height times area. So sum of height times area. The most basic kind of volume calculation is a prism, some sort of base of a known area, times the height is the volume, and then sum up the pieces. And the idea should be that as these pieces get smaller and smaller, this is going to become a better and better approximation, and in the limit, it's going to work. So you'd say equals the limit as, and I don't have much room to put it here, let's say roughly as delta A goes to 0. You have to be much more careful about that if you're going to prove things really carefully, but basically as those pieces get smaller. So this is one way to do it, and one of the really important things about talking about this in this level of generality is I don't really even need these to be rectangles. As long as there's some systematic way of dividing this region up into small pieces and making the pieces go to 0, this is going to work. Sum of height times area where they're just any small pieces. They don't even have to be rectangles. In particular, I could have a situation, ooh, I don't want to erase that. I could have a situation, we're going to see this situation later, where the floor plan, maybe the floor plan is like part of an annulus, the region between two circles. Everything in here. Dividing this into rectangles is a bad idea. It's better. It's going to be better to use polar coordinates. And this was basically using the Cartesian coordinate grid. You could use the polar coordinate grid and look at the places where r is a certain number, and this is where theta is constant, and divide it up into these little wedges of circles, basically. These are totally legal little pieces. You can calculate their area. It's not too hard. They're just wedges of simple things of circles. And you can exactly write this kind of thing down. And so that's going to be integration in polar coordinates, which is coming pretty soon for our class, and almost any class if you're watching this video. And you could do all kinds of creative ways of dividing things up. Certainly rectangles and polar grids are by far the two most common, but it's a very, very flexible idea of sum of height times area, sum of height times area, and then take the limit. Now, just like in BC calculus, or one variable calculus, we don't actually do the calculations that often in this way, but this is where they acquire their meaning, and this is a good way to talk about how flexible the idea is. Now, in terms of actually doing a calculation, back to our particular example right here, integral over r of 8 minus x minus 2y dA. Okay, so now that's what the dA means. It means that anyway, it's the idealized infinitesimal version of the delta A, and the sum is turned into an integral, and there's the values of the function. It's to remind us of this idea that we're slicing up the floor plan into any kind of tiny, tiny little bits, and we're imagining them as being infinitesimally small. But you don't have to make sense of that in any concrete way. It's just a suggestion. And taking the sum of height times area in any way you want. Now, practically speaking, a lot of the time, you go ahead and realize that slicing it up, that putting it into these rectangles, you can think of them as, okay, I'm going to put all these rectangles into a slice, I'm going to put all these rectangles into a slice, I'm going to put all these rectangles into a slice, and you get back to the iterated integral idea, which is where we would explicitly say, okay, I'm going to do this as like dy dx, 8 minus x minus 2y, and this is x is going from 1 to 3, and y is going from 0 to 2. This has gone from the double integral idea, where I wasn't particularly interested in introducing coordinates, I just used an abstract letter r, and I didn't commit myself to any particular way of describing the area. I could have been thinking about polar decomposition of this region, or dy dx, or dx dy, or all kinds of things. And here I've committed myself to a particular way of calculating it, in particular an iterated integral, and in the order dy dx. And then I can actually get a number out of that guy. Not too hard to go through and get the number. And I kind of hate not to do that, but I don't want to make the video too long. Okay, so, and that's going to be that volume. Many other things calculated by this, but you certainly can think of this as the volume of this house. So, I want to just emphasize this connection between the geometric idea, the calculational idea, which is usually going to be some sort of iterated integral, and the very general idea of the limit of a sum of height times area. So the second thing I had on my to-do list was net signed area, just like, or net signed volume, just like in one variable calculus. The idea of the volume of this always being an honest-to-God volume is a little limiting, because that only makes sense when you're integrating a function that's above the xy plane, that has positive values. And so let me actually extend the floor plan here. Let's extend the floor plan to y equals 4. That's going to take this guy out to here. Uh-oh. That's where this plane is diving down under the xy plane. Okay, because this thing is going to be 0 when x plus 2y is equal to 8. That's going to create z equals 0. And that, let me do it in the floor plan here. Here's 4, and then 8's going to be a bit off there. It's going to be like this. It's going off to x equals 8. So here is where the function is positive. That's corresponding to this guy. And then up here, I'll put like little dots in. That's where the function is negative. So our height of our, quote, roof, unquote, in this region here is going to be negative. So if you did, let me make some room here. If you did the integral 1 to 3 in x and 0 to 4 in y, that's an 8 still, okay. That you really can't literally interpret as a volume. It's the net signed volume. Between the xy plane and the surface z equals 8 minus x minus 2y. And in the next video, I want to talk a little bit about, why would you do that? There's so many reasons, but I want to look at a really basic reason why you do that, and I want to explain that using average values. Let me just justify real quick, though, why this connects to the Riemann sum idea. The Riemann sum idea, remember, is you take the sum of f of values on each little piece, and now we're dividing this whole thing up, times delta A. If I do this, all small, I'm just going to say all small pieces because they don't even have to be rectangles. If you do this as an approximation to your volume, unless you go through a lot of hoops, you're going to get a negative contribution. Whenever this is less than 0, you're going to get a negative contribution for that. So it's not going to just add up a bunch of positive numbers. When this is negative, and that's when the graph of f is below the axis, like here, as this is slicing down through, you're going to get a sum of positive numbers where it's above and negative numbers where it's below, and there's going to be some signs and some possible cancellations, which is what the net means. Okay. You could, if you really wanted to, if you said, I really just want volumes, I could put absolute values around this f, and I could put absolute values around here, and I'd be integrating an absolute value. That's totally legal. We do the analog of that in BC Calc. But the annoying thing is that the algebraic procedures and the kind of fundamental theorem of calculus procedures that we use to calculate integrals hate absolute values. Because absolute values are a trick. They just say, let's do this piecewise. So you could put an absolute value here, but it really means do it as two parts. Do this, counting it as above, and then take the part where the plane is slicing below and flip it up, and then do that separately. So if you think that there's an easy solution there, it's really just a trick. You're going to have to split it up into pieces. And that happens. We definitely have situations like that. Okay, so that's where I want to stop this video, but the very next one is I'm going to talk a little bit more about a good example where this is a really reasonable thing to calculate and relate it to the notion of average values.